Section 2.2, we're going to learn about velocity. And in addition to velocity, we're going to learn the difference between velocity and speed. And we're going to see that there are two types of velocities, the average velocity that we will define and the instantaneous velocity. So we'll learn about all these things. We'll also learn how to interpret information from a graph in order to get both the instantaneous velocity and the average velocity, maybe from a position time graph, okay? So first, let's look at scalar and vector quantities. We talked a little bit about vector quantities when introducing the idea of displacement. A vector quantity essentially has a magnitude, which means its value or size, okay, and a direction. In a one-dimensional motion, the direction can simply be given by a positive or negative sign. If it's positive, the direction is to the right. If it's negative, the direction is to the left of the origin, okay? And when we write a bold typeface, that's the symbol we use for a vector quantity. Okay? Sometimes when we write on the board or when we write by hand, we may have no way to bold something, in which case we put an arrow over the letter. So these are symbols that something is a vector as opposed to a scalar. And the positive or negative sign, we already talked about this for the direction. So scalar quantities, in comparison to vector quantities, are just a number. They may have a unit attached to it. For example, 20 meters. It could be 20 meters in any direction, right? Starting from anywhere. So if I just say go 20 meters, you don't know whether to walk north, south, east, or west, or northeast, or north, northwest. You don't know. So I haven't given you a direction to walk in. I just said walk 20 meters. That's a scalar quantity. As opposed to a vector, well, I'll say walk 20 meters to the east, okay? So we have a common feeling about the term speed. If I say, what was your speed driving to work from home? You might take your total distance, say 30 miles, and it might have taken you 30 minutes to drive. You're going to divide the total distance, 30 miles, divided by the total time, half an hour, and calculate your average speed, right? So average speed is just the entire path length, which is the total distance that you travel, divided by the time elapsed, the time it took you to cover that path, right? So we might write this as v equals d over t, where d is the total distance for the path length, t is the time elapsed, and v, note that this is not a vector quantity, does not have an arrow, is not in bold. So that's just the average speed. It's the magnitude of the velocity. Yeah. So speed is a scalar quantity. It's going to be given by this number here, along with some units. It might be miles per hour. It might be meters per second. Okay, in the SI unit, it's going to be meters per second. When you give an average speed, you totally ignore any variations in your trip. For example, at some points you might have been driving at 60 miles per hour. At other points you might have been stopped at a traffic light. Somewhere you might be in a school zone at 20 miles per hour. But you're just going to give an average of all this. You're not going to tell me anything about those variations in between. Okay. Similarly, the path length is going to be the total distance traveled. If you double backed on yourself or you took a U-turn, there's no information about that when you calculate the speed. Okay? So speed is always a positive number. You're always going to cover a positive amount of distance divided by a positive amount of time. You cannot go back in time, and you cannot have a negative path length. Path length always has to be positive. So that was speed. We're going to compare that to velocity. Remember, velocity is a vector quantity. And we're going to define velocity as our change in position. But we've seen what is change in position before. Change in position with time is our displacement, right? So here's my change in position. This is my displacement, delta x. Remember, that was x final minus x initial, the final position minus the initial position. And when I divide it by the time taken, so delta t, that's final time minus initial time, that's going to give me my average velocity, okay? So here we define our first type of velocity called the average velocity, is the displacement divided by time. So rate of change of displacement, okay? And it can be positive or negative because although the time is always positive, the numerator could be a positive term if xf is a greater absolute value than xi, or it could be a negative term if xf happens to be a negative number and xi is positive, or xi is a small negative number, okay? So velocity can be positive or negative. Xi could even be a large negative number. Delta t is always positive. The average speed is clearly not the same as the average velocity, since we saw that the path length is a different thing from the displacement, right? So we saw that before. Okay. In what units will be our average velocity? We're going to give it in SI units, which is meters per second. Okay. So you may have conversions required if you do problem solving, from miles per hour to meters per second and so on. Okay, just to illustrate the difference between speed and velocity, let's consider this example here. Two cars, a blue one moving along the blue path and an orange one moving along the orange path, start and finish at the same time. So they both start at P and they both end up at Q at the same time, okay? What can you say about the speed or velocity about these two cars? So first, let's consider speed. For speed, remember, we need to look at the total distance traveled, or path length, divided by elapsed time. So the elapsed time is exactly the same. They start and stop at the same time. Okay, so there's no difference in the denominator. What about the numerator? This is the shortest distance, the orange one, between P and Q. So this is the shortest path length. Clearly, the blue path is longer, which means the speed of the blue car has to be faster for it to cover this greater distance in the same amount of time, right? So we can say that the speed of the blue car is greater than that of the orange car. Now consider the velocity. So how do we define velocity? We have the same denominator of the elapsed time, okay, time difference, time final minus time initial. It's the same for the two cars. No change there. What about the numerator? It's the displacement. Is there a change in displacement? Is the displacement different for the blue and the orange car? This is what you must ask yourself. Indeed, no. Their final positions are the same. Their initial positions are the same. So they have exactly the same displacement over exactly the same amount of time. Hence, their average velocity will be exactly the same. Okay. In general, we can say that we can find the velocity by interpreting a position time graph, and we're going to look at some of these. If we take the slope of the line joining the initial and final points in the graph, then we will find the average velocity, okay? And let's have a look at that. So here's my position time graph. Remember, position on the y-axis, time on the x-axis, because this is the second term I said. Position, time, graph. Time is in units of 10 seconds again. Here's my origin. So we're starting to the left of the origin. Then we go through the origin in 10 seconds. And in 20 seconds more, we are at positive 40 position. So if I consider A and C, what is my displacement? My final is 40. And I need to subtract out negative 20. So that's going to give me a positive 60 over how much time? Over 10, 20, 30 seconds. So 60. So it's going to be 2 meters per second. Now, it's going to be my slope here. Okay, and that slope, 2 meters per second, is telling me my average velocity. Okay, so I have a fixed average velocity because this line has a fixed average slope. Okay, so a straight line indicates a constant velocity, a constant average velocity. Okay, and that velocity is given by the slope of the line for the position time graph. So slope was the change in vertical axis divided by change in horizontal axis. This is my displacement. and this is the elapsed time. Okay. Let's look at another one where it's not moving at a constant velocity. So this is another position time graph, okay? And this goes from A to B to C, D, E, F. This is actually the previous car that we had seen in an example before in the displacement case. A to B, it's not moving in a straight line, it's moving along this curve, okay? However, at a given point, let's say point A, it starts off with a certain velocity. So if I draw a tangent to that curve here, okay, which is this green line, it touches this curve, orange curve, at a single point, which is this point A. The slope of that green line tells me the instantaneous, the velocity at that instant, right? And what does this blue line tell me? The blue line is connecting this final position B to this initial position A, let's say, for this part of the journey, okay? So I'm going to get my average velocity between A and B given by the slope of this blue line. This is my displacement change on the vertical axis. This is my time change along the horizontal axis, which is 10 seconds. And that's going to be, the slope is going to be rise over run, and that's going to be a certain number of meters per second. It's going to give me my average velocity. So the slope of the blue line is telling me my average velocity. The slope of the green line here, which is a tangent line, is going to tell me the instantaneous velocity. What about this line? This is going to tell me the average velocity between the positions A and C. If C was my final position, then the average velocity between A and C is this. This has actually got a shallower slope, right? So overall, the car moved a lot slower from A to C than it moved just from A to B, yeah? Because it actually double backs on itself. So the change in displacement is less. What about A to D? This has actually got a negative slope, right? The car is moving in the opposite direction, to the left. My displacement is negative. A to the very final position, F, again, it has a negative slope. This is my average overall velocity in the car being displaced from A through all these positions to F. So we touched briefly on instantaneous velocity. Instantaneous velocity is the velocity at a particular instant in time. So if for now you forget about this middle part, I say my velocity was given by displacement, delta x, divided by delta t. So this is x final minus x initial, t final minus t initial. And if I make the change in time very, very, very small, approaching zero, then I can say that in the limit delta t tends to zero. This is how you read it. In the limit delta t tends to zero, delta x over delta t is going to give me the instantaneous velocity. Yeah? And this is bold, this is still a vector quantity. The three lines here means this is equal to this by definition. Okay, so this is a definition when you see three lines. Okay. In general, the magnitude of the instantaneous velocity is what you're going to see on your car's speedometer. It keeps on changing as your car starts, stops, accelerates, you go at different velocities, that number keeps on changing, right? Okay, so you don't see the average velocity, you see the instantaneous velocity in your car's speedometer. And we touched briefly that the tangent line to a position time graph is going to give you that instantaneous velocity. So here's a graph that I hope makes clear the difference between average velocity and instantaneous velocity. It's a position time graph. Remember, to get information about my velocity, I need a position time graph. Then I'm going to look at the slope between any two positions. And if I take this position here and that position there, and I join them with this blue line, I want the slope of that blue line. I could extend it out, doesn't matter. I get the slope of that. It's going to tell me what kind of velocity? It's going to tell me the average velocity between these 2 points. Just like between these 2 points, this is the straight line joining them, and the slope here is going to give me the average velocity between these 2 points. Yeah? What about the green line here? The green line, maybe let's say a tangent at this point, which means it appears to touch the line, not appears, it touches this orange line at just one point here, this point. So it may not seem so from this graph. That's just because the scale is reduced. So it appears like it's touching at more than 1 point. But if you blew this up, you could zoom in, you would see that it touches at just 1 point. That's what's the meaning of a tangent. Then the slope of that tangent line, the green line, okay, would be the instantaneous velocity at the point at which it touches. So at that time of 1.2 seconds, that would be the slope of the green line would be its average, or its instantaneous velocity. I beg your pardon. And you see that that instantaneous velocity is slightly greater than the slope of this blue line here, which joins these 2 points, which is the average velocity. Okay. Doesn't have to be greater. We're just noting that from the graph.